Welcome to this lecture and practical demonstration on vulnerability discovery and exploitation. I want to focus on binary fuzzing, and this is something that you may find useful to do for your coursework. I don't expect you to actually find any additional vulnerabilities through this process that you couldn't find via essentially static analysis, via inspection of the code, or testing things out for yourself, knowing the function of the code. However, one of the things that I'd like to demonstrate is, as we continue to look at fuzzing, I'd like to talk through the process of setting up and running fuzzing, and there's a word that's used for that. It's called instrumenting binary files. So last week we covered generating files using a fuzzer. So we're generating files that had randomness added to them, either in the bytes that were the files contained, or in the size of the input areas for those files. Now we're going to go through the process of compiling from source code, and in the compilation process we're going to add some things to the binary file that's called instrumenting, that will be useful for testing out for vulnerabilities later on. So one of the things that you're already familiar with in finding flaws, so what you're pretty much already doing is looking at the code, looking at the functionality of the code, so doing a design review, reviewing the code itself, a code review, performing some form of static analysis, and performing some form of dynamic analysis at runtime. Now, we're introducing this concept of fuzzing that we started last week, so where we're randomizing our inputs, and it is surprisingly effective. So it's one of the things that I think is important to cover when looking at the discovery of vulnerabilities in programs. Now, as a general background, when we go through the process of fuzzing, we're interested in picking a target. So it's picking a target binary and executable that we're interested in finding vulnerabilities in. We're identifying the fuzzing attack surface, or we're identifying the inputs, where those inputs are formed into that target. We're then going to pick a tool or write our own tool. So for the sort of stuff we're doing last week, it's very easy for you to write your own tool. For the stuff that we're going to look at this week, it's much more difficult, because we're essentially making changes in the compilation process. You then need to go through the process of making your tool and your target work together. And then you start fuzzing, and then when you finished when you finished trying all of the possible combinations you were looking at, you then go through the process of triaging, of checking the results to see what happened. Now we're going to use a tool called American Fuzzing Lot. This is a security-oriented fuzzer. It employs a load of compile time instrumentation, so it adds things to the binary file that's being generated. It then uses a set of algorithms, some of those genetic algorithms, to discover clean and interesting test cases that trigger new internal states in the targeted binary. So it is both an instrumentation, so it's a compilation process, as well as a fuzzing process, so identifying all of the new states that you could possibly test. Now, what we're interested in doing, as we started off talking about last week, is producing a seed corpus, so producing files that exhibit particular properties, and those properties are, they have unique attributes, so they will test different things within the program code. It is possible to build your own inputs, so whenever you have the input, whenever you have the source code, you can see how those inputs are processed. Whenever you have examples, because your application is taking standard file types, then you can use some of those standard file types. It's good to keep files small, so under 1 KB is ideal. And it's absolutely useless testing or having different test cases if there's no difference in the functionality. So there's no point in adding or using 50 different vacation photos if every single vacation photo tests exactly the same steps in the code as the other ones. Now, there are some limitations to AFL. It will only identify crashes, so it will only identify memory issues. It will take input only from standard in or from files. It will only work on Linux at the moment. In order to get the best results, you need to build your target binary from source using the compilation process that AFL has built into it. It is possible that it gets stuck on magic values. Certainly some of the things that I've done in the past with it, I've had output crashes, so the test cases that cause the application to crash were interesting because they contained magic values rather than the sort of things I was expecting. And unfortunately, it is incredibly slow, and there is no native parallelization using AFL. Now, what I want to do now is just run through a very quick demo. So I'm going to go through the practical. The practical contains this very simple code. I have a main function. It calls a names function. My names function has two statically declared arrays. Though into those arrays we're putting some user input. We're not checking the size of that user input. We're not checking any validation at all on that user input. So we have a fairly standard stack-based buffer overflow here. We're going to compile using the compilation AFL Clang. So we're using Clang as a part of the compilation process, and we're using the fast version of this, which just is optimized for possibly slow programs. Now, if we have a look at the practical, so what I'm asking you to do in this fuzzing lab, it's a step-by-step walkthrough for simple program fuzzing. You're going to need to set up your system. So if you're using Ubuntu, you will need to run all of these commands. So you need to set up Clang, you need to set up all of these update alternatives. We then need to go through the process of ensuring that our system isn't going to interfere with any crash detection that our kernel is going to process. So we're going to echo core into our /proc/sys/kernel/core pattern. And then we're actually going to get American fuzzing glops. So we're going to get AFL. We're going to get that from this web link here. You then go through the process of unzipping and untarring it using this command. That would generate a folder, and in that folder you go into that folder, make -c for LVM, and after that you can execute sudo make install, and all of that should compile and set up AFL perfect for your system if you're using exactly the same system that we have in laboratories, which is Ubuntu 18. Once you've done that, I've tarred up a standard directory that I'd like you to copy. You can then go through the process of compiling your the C file that I've given you, and then setting up fuzzing. And then once you've done that, I'm just saying have a look at the results. So I'm going to have a look at some of the results now, and then instrument the core sort programs 1 and 2 for AFL and go through the process of testing them, see what happens. So let's have a look at my Ubuntu system. And in my Ubuntu system, I have terminal ready. I already happen to be in the AFL-2.52b folder. I have gone to the web link. I've downloaded the tar file. What I'm going to do now is I'm just going to copy that because it's saved into my downloads directory. So I'm going to copy it from downloads. Simple program.tar. I'm going to copy it to my current directory. Now that I've copied it to my current directory, I can have a look at the contents of my current directory. And you can see in my current directory that I have AFL-clang-fast, which is the compiler that we're going to use. I have AFL-cmin, AFL-tmin, and both of these can be used on a set of input files in order to reduce the size of the input file and to reduce the number of input files. So the sort of things that you would have generated from last week, you can have that as an input. You can have AFL optimize your input files in order to make sure you don't have anything that overlaps. But what we're interested in now is actually the tar file that I've just downloaded. So I'm going to untar that. And once I've untarred it, as you can see in my directory here, I have the simple prog directory. If I change directory into that, what you can see is that I have one directory in there. I have a make file and I have my C file. So the C file is the one that you already have seen. I have two includes. I have my function prototype for names. My main function calls names, and in names I have these two statically declared arrays taking input from the user. I then have a make file, and this is the first time we've used a make file. So in my make file I have some flags, my compilation flags, -G as you're familiar. So I have symbols, and if I'm going to do some GDB analysis, I have -W again if you're familiar, so I can suppress any warnings that I might get. I then have this is set up for the test binary which is produced, so syntax you should be fairly familiar with. The only difference is that what we're doing is I'm going to be passing in the command line a value for capital C, and I'm passing in my C flags that I'm generating from up here. So this whole command line you should be very familiar with. The only difference is we're going to use make in order to make our binary file. Now, if I then have a look at my inputs directory, we can see in the inputs directory that at present I only have one file. If I have a quick look at that file, what I can see is I have two words. One is Steve, the other one is Jones, and these will serve as input into the binary file that is produced. So that's the layout, that's the structure of my standard AFL sort of fuzz directory. So if I'm going to add anything else, I'll need to make adjustments to the make file, and in the make file I'd need to change whatever the binary is called, and I need to change my input file name. I would need to have my input file available to be used, and I need to set up my inputs directory to include either one sample file or multiple sample files that I'm going to test the inputs to my programs. If I want to go through the process of making a binary file, then I'm going to set up, as we were looking earlier, I'm going to set up this CC value to being equal to AFL clang fast. I'm actually going to set an attribute here, harden 1, which just makes it easier to find some memory vulnerabilities, and then I'm going to type make, so I'm going to access the make file. This should then go through the process. What it does is it instruments two locations. So these two locations are going to be the input locations, where I'm asking for the forename and I'm asking for the surname. If I then go through the process of running the binary file that's just been generated, I have something that says, please enter your forename, Nick, please enter your surname, Smith, hello, Nick Smith. So you can see the functionality of the program. If I run the program again and just type in lots of gobbledygook, and then type in lots of gobbledygook for the surname, it's irrelevant what I'm doing here, but because I have this AFL hardened, I've got this stack smashing detected here, so I've put in some protection around various bits of the memory to identify that. So what we're really interested in is we're interested in now using AFL fuzz to test that simple program. So I can execute AFL fuzz. I can tell it that the input file types is located in the inputs directory. I can tell it that I'd like it to generate a directory called outputs, and in the directory called outputs it would have all of the output files. So my -I is for input files, my -O is for output files, and then the binary file that I'd like it to test is the binary file that I've just generated. When I click go, we can see that bear in mind I'm running in VirtualBox here. I have some crashes. I have one unique crash. Let's just go and have a look to see what caused that to happen. And now if I have a look at my directory structure, I have this outputs directory, so let's cd into that and let's have a quick look to see what's there. I have a directory called crashes, a fuzzing bitmap to see how much of the application how much of the path we fuzzed, hangs and queues. Now I'm interested to have a look at the crashes, so if I just cd into that directory, have a look to see what's there. So I have a readme file. The readme file tells me essentially what was used in order to execute AFL fuzz, and the other file that I have there details the input that was used in order to cause this to crash, which is slightly odd. That input doesn't quite look like it would cause a crash until we have a look to see what the input actually is. And what we see here is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 bytes of data. What we do have though is we see that we have this null here. So we have the first part, which would be the forename, and the second part is then used presumably in order to emulate the entry point to the second into surname. So that's an example of using AFL, of instrumenting a binary file and then executing that binary file and using AFL fuzz in order to fuzz some of the inputs. If I just go back to my presentation quickly, I think I had a couple more points that I wanted to make. As we go through, AFL is able to track the paths that it takes, so it is able to identify the execution paths, which will be different to get from, let's say, A to E. It'll be able to tell the difference between going through C to D as opposed to D to C on an execution path. So it is able to identify what paths it's taken, what paths it's executed. And it is possible to go through the process and find bugs. So Heartbleed is a read buffer overflow. It doesn't lead to a crash. However, AFL will add characters that compile time around variables to see if they are hit in the same way that stack smashing does. So we can identify heap overflows in this format. The last thing I'd like to say is it is possible, as I said, to use AFL tmin. Here are some examples of using tmin in order to reduce the size of the input files, in order to reduce input files with the same functionality, to reduce the number of input files. And I've got an example there of how to execute the command. Okay, thanks for listening.